Hello, everybody. I am Esteban Carisimo. I'm a postdoctoral researcher at Northwestern University, and today I'm going to present our work, which is about using PeeringDB to enhance AES to organization mappings. This work was done in collaboration with Augusto Arturi and Fabian Bustamante. So we are going to begin our presentation by looking at the AES level topology as the one that we have in this example. Here, the clouds represent AESs, and the lines show interconnections between these AESs. So the AES level internet topology has been vastly studied over the years, and there have been substantial efforts to understand AES relationships. But one of the problems of the AES level perspective of the internet topology is that AESs do not subscribe to interdomain agreements. These agreements are subscribed by the companies operating these AESs, which in this talk we're going to indistinctively mention as organizations. And the thing is, the organizations or companies sometimes operate multiple AESs. So one solution to this problem from the AES level representation of the internet topology could be to look at the internet topology from an organizational level perspective. Here we have different colors that represent different organizations. And as you can see in this example, one organization can have multiple AESs. So the question now is why organizations have multiple AESs. In some cases, this is to assign different AES numbers to different subsidiaries, or in some other cases to different business units. The use of multiple or AES numbers under the same organization can be also part as from mergers and acquisitions. These are legacy resources after two companies merge. So what is our goal then? So our goal is to identify siblings or AESs under the same management. And we can see that this problem has been studied before, and the current state of the art of technique uses quiz records to identify sibling AESs. But as we're going to present in this talk, quiz records face a lot of challenges, and we propose to solve or to overcome some of these challenges by using PeeringDB. PeeringDB is an operator-oriented database that could provide a complementary view of the problem. And as I was saying, Quiz faces a lot of challenges to identify sibling AESs, and we're going to discuss a few of them now. One example is that large corporations separate their business units into different legal entities. And different legal entities are going to have different organization IDs given the allocation policies of the RIRs. And this is the case of Claro, a large mobile operator that operates in Latin America. And these are Claro's subsidiaries in Argentina and Chile. And we can see that them have different organization IDs in Quiz records. Another problem is outdated records. For example, this is Liberty. Liberty completed the acquisition of Movistar Costa Rica in 2022. And Liberty has even rebranded Movistar Costa Rica as Liberty. But if we go and look for the Quiz records, we're going to find that this records does not show any change, any updates since Liberty acquired the company. So there are many other problems that we describe in the paper, and we invite you all to look at what we explain there. And one of them could be real IRR level allocations or use of companies' legal names. But we now propose to take PeeringDB to overcome some of these limitations. And we have identified several challenges and opportunities in PeeringDB. We can discuss about the limited coverage that PeeringDB has. It only covers now 34% of the AESs active on the internet. It does have geographic biases, or we can discuss about completeness, correctness, and the use of fields. But despite all these problems, we have identified good opportunities to identify sibling AESs in PeeringDB records. And this is one example of a PeeringDB record. This is for GTT AES 4436. And we can see multiple opportunities here. The very first one is all PeeringDB records have an organization ID for the networks. This means that organizations can group together all AESs under the same organization ID. Another interesting thing, as we can see in this second example, is the field also known as which operators sometimes use to show or to communicate information about their siblings. For Telecom Argentina, we can see that the operator is saying that this other two autonomous system is under the control of 7303. I'm going back to the previous example. Now we are going to focus on the nodes, which is typically used to communicate more information, and that extra information could also be about siblings. We see that this AS was acquired by GTT, and it's sharing the information, the autonomous system number, of both the parent company and this AS as well. So by knowing that these three fields are present very good opportunities to identify sibling information, we create this framework, which is AS2WOR+. So our idea is to use AS2WOR+ to extract sibling information embedded in PeeringDB records and combine it with the inferences of AS2WOR+ with pre-existing AS2WOR methods. So in the next slides, I'm going to explain the role of each of the four stages in our design. As I was saying, we're going to extract embedded information, and we're going to combine it with AS2WOR methods. So the very first step that we develop is to extract information embedded in these records. Here we have three examples, one for the org ID, one for the nodes, and one for the AKA. And the idea is to convert all the embedded information here into this format. So this is very straightforward for the org ID. The structure is very simple. The data is structured in a way that is simple to retrieve the autonomous system numbers under the same organization. But for the nodes, it's not simple, and for the AKA, it's not simple as well. We need to develop some pattern extraction rules or pattern recognition tools, in fact, to extract this information. And for that job, we develop approximately 40 different regular expressions that capture common practices used by operators to communicate sibling ASs. But these techniques sometimes have challenges, so we develop custom filters to mitigate the impact of these challenges. So one of the challenges here is sometimes the lack of context. We as humans, we can identify whether a number is an autonomous system or not, but this is very hard for the methods we use here. So one of the problems is that the regular expressions could identify unrelated numbers as autonomous system numbers, or sometimes their nodes communicate ASNs or networks under different management, but it's part of the extra information that operators want to communicate. For example, partnerships. Some ASs partner with AS42, and that is included in the nodes, but AS42 is not going to be a sibling of the network that is communicating that. But the main problem is here is the upstream providers. In a very few cases, network operators share the whole upstream connectivity that they have, which is, as in this example. And of course, all these companies do not belong to the same organization. So to mitigate these challenges, we developed three different techniques. The first one is an sparse number filter, which is going to exclude all numbers that typically appear that do not correspond to sibling ASs. A customer to provider filter that is going to allow users to decide whether or not to include upstream providers. And the very last one is manual inspection, where human operators, the users, can determine whether to insert or remove ASs from the clusters inferred. So as I was saying, this is the third stage where manual inspection is conducted. All users can remove or insert ASs in the pipeline. And the last stage is a data consolidation stage, where we combine PeeringDB inferences with AS2WOR methods, but it's not only that. We need to include it for one more reason. In some cases, operators copy-paste the same information across all nodes under their control without cross-referencing each other, as in this example. As a result, in these cases, no entry draws a complete representation of the organization. So we then develop a consolidation stage where all the scattered information is grouped together. So this is the end of the pipeline, and now we're going to evaluate this. So to evaluate the contribution of AS2WOR+, we apply it to a 5-year dataset. This 5-year dataset uses a single day snapshot, which are in different years, across 5 different years. And we evaluate this as we show in the table. And what we found is that each feature contributed to the tech organization's clusters, including non-atomic ones, meaning clusters of organizations that operate more than one AES. So we also analyzed the overlap between the clusters generated by each of the features, and we discovered very little overlap, showing that each features provide a unique contribution to the AES2 organization problem. But however, the main contribution that we have is the enhancement of pre-existing organization mapping techniques. What the highlighted column shows is that up to 4,000 AESs are now in different clusters. So 4,000 AESs now belong to a cluster that has a different representation that was not able to generate without PeeringDB data. And to conclude our evaluation, as a very last step of this, we studied the practical implications of AES2OR mappings. We investigate the contribution of AES2OR Plus to organizations serving and delivering significant fractions of the internet traffic. Here we have the AES rank. So we look at the transit networks. Here in the gray line represents the cumulative reclustered AESs, and the dashed lines show the linear regressions for some sections of AES ranks. And as we can see, the AES2OR Plus draws a more complete representation of organizations, but in particular, we see a different slope for AESs leading the KDAS AES rank. So AES2OR Plus also enhances the representation of hypergiant organizations, large content providers, and content delivery networks. As we can see in this example, AES2OR Plus draws a more complete representation of Google and Akamai. This is because our method includes in the same cluster Google Cloud Provider and the rest of Google's organization. And similarly for Akamai, that now includes Prolexit into the organization. So to conclude this representation, I would like to highlight the contributions of our work. Our work presented AES2OR Plus, which is a new framework for AES2 organization mappings. This framework is based on self-reported information that is available on PeeringDB. In this work, we have identified common practices used by operators to report AESs under the same management. And we combined all this information in AES2OR Plus to generate better representation of the organizations. And we validated this, and we found practical implication of this better representation that applies for large transit network, hypergiants, and multinational conglomerates. So thanks for attending to this virtual presentation. We invite you all to read our paper and to visit our GitHub repository. Thank you.